Hi everyone, my name is Benjamin Lee, and I will talk about how graph theoretic approach can be used to simplify the control change when a system is under a failure mode. So the system we will look into is a hexapod walking robot, which is a locomotive robot with 6 legs. There are 3 joints in each leg, and the coxa joint is the joint that is attached to the body and connects the body to the leg. And the femur and tibia joints are um, within, within the leg and takes care of the vertical movement of the leg. And a typical gait of a hexapod robot is a alternating tripod gait, which means 3 legs are in swing mode and 3 legs are in stance mode. So in every step, three legs will be swinging and the other 3 will be stabilizing the robot. The failure mode that I will introduce here is called locked joint failure, which simply means a joint is broken and is no longer controllable. So in case of the coxa joint failing, we will no longer have the horizontal rotation, which means the forward swing motion is completely taken away while the robot is walking. And when the femur and tibia joint fails, the vertical rotation is no longer available. So the reachable workspace of that uncontrollable leg is considerably shrunk. And the new shrinked workspace resulting from failures can be implemented as the physical constraints in an optimization problem. So I will introduce a graph model of a hexapod robot that consists of the body in the middle and the 18 nodes that are numbered as follows. So why do we consider graph model? In order to model the locked joint failure, graph models can represent complex systems with simple structural information such as the nodes and the interconnecting edges, and the internal system behavior and integrity can be evaluated, rather than looking at the whole complex model in the entirety. And we can see that the hexapod robot has a star graph model, which means it is centered at the body, and the nodes around the body has higher dependency, meaning more edges connected to them. And we will see how this affects the graph behavior in the next slide. So some of the graph theoretic elements to be considered are the adjacency matrix and the degree matrix. The adjacency matrix is, in this case, an 18 by 18 matrix where the element at ith row and the jth column is simply going to indicate if the node I and node j are connected with the value of 1, and if they are not connected, it will have the value of 0. And the degree matrix is a diagonal matrix, which is also 18 by 18 in this case. And the diagonal elements will be the dependency of each node, which means the number of edges that are connected to each node. And we can see that the structure of the degree matrix for the hexapod graph model is a repeating block diagonal matrix due to it being a star-shaped graph, meaning the central nodes have higher dependencies and the nodes that are further away from the body have lower dependency. We can develop these two graph theoretic elements to represent the behavior of the system. And we can start with considering the Laplacian and transition matrices. The Laplacian matrix is, in this case, also an 18 by 18 square matrix that describes the system structure. And the formula will be the dependency matrix minus the adjacency matrix. So in this case, the diagonal elements will be the degrees, and the non-diagonal elements are going to be -1 if the node I and node J are connected, and 0 otherwise. And also the transition matrix, in this case, is also something similar to the randomized normal walk, which describes the epidemic spreading likelihood as a random walker on a graph. And the formula is the inverse of the dependency matrix times the adjacency matrix. And so assuming we start with a basis vector E, the random walker's probability distribution at time k will be equal to e to the times the transition matrix to the power of k. And that will be how likely the basis vector will spread out to each state transitions at time k. And the higher the dependency of the node means higher it will have higher probability of the epidemic spreading, which means other effect from other nodes is more likely to be transferred to that node. And we will also consider algebraic connectivity as the standard for resiliency of the system. The algebraic connectivity is the second smallest eigenvalue of the Laplacian matrix, and it indicates the graph's overall connectivity. And using the dependency and adjacency matrices from the hexapod graph model, we can see that for the hexapod robot case, when there is no failure mode and it's operating normally, the second smallest eigenvalue is 0.3384. And now we will look at how the effect of failure mode affects the algebraic connectivity. So if we look at the case of one, so to start over, when a joint is under locked joint failure, meaning it is no longer controllable, that faulty node just simply becomes an edge, and the adjacency and degree of the corresponding failure node will go to 0. And in the case of one failure mode, let's say node 8 is no longer controllable, we see that the algebraic connectivity reduces down to 0.04874. And when another joint is failed, let's say node 15, the algebraic connectivity it simply approaches 0, and that means the system is in an algebraic sense, it is disconnected. So for this project, we will consider the failure mode of one locked joint failure. So in case of a locked joint failure, the shrunk workspace of a leg with locked joint can be compensated by adjusting the other leg's workspace with different horizontal and vertical joint actions by adjusting the rotational forces of the joint. So assuming we want the hexapod robot to travel from point A to point B in a straight line, when one of the joint is failed, the robot will initially move in a path that is not on the straight line, but will eventually adjust the other joint's rotational forces to move back to the desired path. And the goal for this project is to find the change in optimal joint rotational force distribution using the random walk probabilities rather than looking at the whole system dynamics again in the case of failure mode. So the Markov decision process for this case can be constructed, and we will have the following assumptions. So we are just looking at a simple objective of going from A to B, and our goal is to maintain the walking stability. So we want the robot to walk in a stable manner, and we are assuming that we have the dynamics model of the hexapod robot, and we will assume that when a failure mode happens, so when a joint is locked, we will know which one is failed. And we will assume that the dynamics are fully observable, so that the position of the robot will also mean we know or the other way around, the joint rotational forces will give us the position of the robot. So we can define the 18 states of joint angles. So it just corresponds to the 18 nodes, and we will just use 3 different joint rotational forces that are available for each state, and those are going to be high, medium, low. So high rotational force we can just say the joint will move with a greater torque, and the angle will change more. And for the low action, we will say the joint will not go through as much action. So we can assign the cost at each joint angle state transition that is proportional to the transition matrix that mentioned before. So that will mean higher dependency node will have higher cost of control. So it is going to be less easier to manipulate. And we will use the value function iteration method learned in class to find the optimal policy for maintaining system stability under failure mode. So when the robot is operating normally, the value function evolution of the 18 states is shown as follows, and the optimal actions at each node at the beginning is shown in this slide. And comparing this to the case when a locked joint failure happens, which is in the next slide, we can see that without having to redefine the whole failure mode dynamic model, we can find the we can find the new optimal policy that corresponds to this locked join failure at node 8 by simply applying the change of internal behaviors of the graph model. And that is how I am showing the simplified method of using graph theoretic approach to compensate for the control change in the case of a failure mode. Thank you.